Hello students, welcome to the final segment of linear algebra and matrix theory. I hope all of you are staying safe. The first topic for this segment will be quadratic forms. Most of you might have encountered quadratic forms already in the second segment, but we'll try to analyze quadratic forms in a bit more detail. Right? After this, we'll move on to positive semi-definiteness, positive definite matrices and positive semi-definite matrices. Again, you have encountered the concept before, but we'll try to understand them in more detail and look at the applications quadratic forms and positive semi-definite matrices have for optimization. Okay, and then we'll move on to some very interesting and very useful results that keep coming up in many different engineering contexts. And then finally, hopefully in the last part of this segment, we will look more into least squares methods. Okay, pseudo inverse and least squares techniques. Once again, you have encountered these already, but we're going to look at slightly more detail, and we'll do a lot of, hopefully do a lot of programming assignments on least squares. So that's the rough plan for this segment, and we'll adapt as we go along. I mean, we may not be able to cover all these topics, but we'll try to do the best we can. Okay? So we'll start this segment with the definition of a quadratic form. Right? What's a quadratic form? So a quadratic form is simply a polynomial in n variables. Okay, that is degree 2 homogeneous. I'll explain what this means. Degree 2 homogeneous. Okay, so for example, a quadratic form in two variables x1 and x2 would be an example quadratic form would be something like this: x1 square plus x1 x2 plus x2 square. Right. So as you can see here, this quadratic form consists of three terms. Okay, each of these terms has degree 2. Right, you can see that this is x1 to the power of 2, this is x2 to the power of 2, and here it's x1 to the power of 1 and x2 to the power of 1. So overall degree 2. Okay, so this is what a quadratic form is. Okay, so quadratic form in general n variables will be degree 2. So for example, in 4 variables, so this is n equal to 2. So when you have 4 variables, an example would be, just writing a random example, plus 30 x1 x4 minus 25 x2 x3. Right, so this is an expression once again that has 3 terms, right, and each term has degree 2. Okay, of course, these coefficients that accompany the terms, here the coefficient is 30, here it's minus 25. We're going to assume that the coefficients are real. Okay, so we're going to assume that the variables and coefficients are both real. Okay, okay, so the variables x1 x2 x3 x4 and so on, and the coefficients, are going to assume that all of them are real. Okay, many of these techniques that we study here can be generalized even to the scenario when they are not essentially real, but they compute to be real. Right, so you don't need x1 and x2 themselves to be real, but you need the overall sum to be real, for example. Okay, in that case, the definition of quadratic form would change slightly. Okay, fine. So that's a quadratic form. It's a polynomial in variables. That's degree 2, and each term is degree 2. That's what it's meant by homogeneous. Homogeneous means each of the terms has the same degree. Okay, so why do you even care about quadratic forms, and why are we suddenly talking about quadratic forms in something that's supposedly a course that's supposedly only supposed to discuss linear algebra, right? So why quadratic? So quadratic forms are very useful in formulating so-called cost functions in many engineering disciplines. Okay, so what is a cost function? A cost function is essentially, often when you're trying to design an engineering system, you're trying to fit the parameters. You're trying to decide what parameters you should pick. Okay, and the parameters that you pick must be such that some cost that you incur is minimized. Okay, that's what is meant by cost functions. And for example, let us say I'm trying to design to use a very simplistic example from signal processing. Let's say I'm trying to design a signal, basically a vector. I'm trying to design a vector x1 x2 to xn. There are some constraints on this vector, right? For example, maybe the value of x1 is already fixed to be like 1, the value of xn is already fixed to be like 2 or something like that, right? And I'm trying to fill in the intermediate values x2 so on up to xn, right? And I want to fill in the values in such a way that the overall vector changes very smoothly from one coordinate to the next. okay, meaning that there is no sudden jump from x1 to x2, there is no sudden jump from x2 to x3, but there are small changes that accumulate globally to give you the transition from x1 to xn. Okay, so in that case, a very natural cost function for you to pick will be something like this, right? So I'm going to x1 minus x2 whole square plus x2 minus x3 whole square, so on, okay, plus xn minus xn minus 1 whole square. Okay, so this is essentially the cost, right? This tries to tell you not to increase x1 minus, not to cause a very sharp jump from x1 to x2, but overall try to make sure that the jump individually from every coordinate to the next is very small. Okay, so then the question that I would ask is how to pick x1, x2 to xn such that this cost function is minimized. Okay, now as you can see that this cost function over here, once you expand it completely, is going to be a degree 2 homogeneous polynomial in the variables x1, x2 to xn. So this is actually a quadratic form, right? And as you can see in this scenario, we're interested in minimizing the quadratic form. We're interested in finding the variables x1 to xn that somehow minimize the quadratic form under some constraints. Okay, for example, here the constraint is that x1 has to be 1 and xn has to be 2. Okay, so often we encounter problems that have to do with minimizing or maximizing quadratic forms under some constraints, right? And that is the topic that we are going to study, try to study in a bit more detail in the next couple of lectures. Okay, to give you another example, suppose that you have a resistive circuit, for example, these are the different nodes and all these connections have some resistors, right? So there is some resistor here, there is some resistance here and so on, and this is a small part of a much bigger circuit or a much bigger network, right? So these are all connected to some other, these are all have some external connections, right? And this is the box that you have, and within this box you have these resistors, and what I'm interested in is the overall power dissipated in these in this part of the network, right? But what would I do? So maybe my variables are the voltages that I'm trying to tune, V1, V2, V3, V4, V5, okay, and the overall power dissipated will be something like V1 minus V2 whole square multiplied with some constant that depends on this particular resistance value, right? So let me just call it C12, the constant, plus let's say C23 times V2 minus V3 whole square, right, plus C24 times V2 minus V4 whole square, plus C45 times V4 minus V5 whole square, right? So these constants, once again, these constants V1, V2, these constants C12, C23, C24, C45 correspond to the inverse of these resistances, right? And V1, V2 are the voltages. So maybe I'm trying to minimize the power dissipated under some constraints on the voltages, because as I said, this is a part of a bigger network. There are some other constraints on how these voltages V1 to V5 must behave, right? So once again, after expanding this, you'll see that this is a quadratic form and you're interested in minimizing a quadratic form. Okay, so quadratic forms are very natural. They come up in many different contexts, as we will see. Okay, note the difference between this quadratic form and this. Here you have every successive difference, but here you don't necessarily only have successive differences. You have V1, V2, V2, V3, V4, V5, but you don't have a V3, V4. Instead you have a V2, V4, right? So it's a slightly different quadratic form. We'll look more at this quadratic form and the relationship to the graph in one of the applications later. Okay, so so that's a quadratic form. So let's try to see the connection to linear algebra now. So it turns out that whenever you have a quadratic form, for example, let's start with this simple quadratic form that we discussed in the beginning, you can try to write it as a matrix product. For example, you can see that you can write this as x1, x2. So I'm writing this as a row vector here, and I'm going to have a 2 cross 2 matrix here. Then I'm going to write column vector x1, x2, the column vector x1, x2. Okay, and let me fill in these entries as 1, 1, 1, 0. You will see why we are filling up the entries like this in a minute. So this is essentially, you can see that by expanding this out, you will see that you'll actually get this quadratic form over here. Okay, I mean, it's very easy to check. I mean, you can easily see that when you multiply this you will get the following row vector x1 and x1 plus x2, and when you multiply it with the column vector x1 x2, you will get the desired quadratic form, x1 square plus x1 x2 plus x2 square. Okay, so it seems that a quadratic form can naturally be written in terms of the matrix, right? So let's call this matrix as A. Then this vector is your x vector that includes all the variables that are present in the quadratic form. So this vector x here has two variables, x1 and x2 in this context, and this is simply x transpose, right? So the quadratic form is just being written as x transpose Ax, okay, where A is the 2 cross 2 matrix and x is the variable vector. So in general, when you have n variables, hopefully we will be able to write any quadratic form as x transpose Ax, where A is an n cross n matrix, x is an n cross 1 vector, and x transpose is obviously the transpose of x, that's a 1 cross n vector. Okay. So as you can see, just by this matrix multiplication, that is actually compatible and all that, and that's how we decided that it has to be n cross n. The matrix multiplication has to be compatible, and overall it computes to a 1 cross 1 matrix or a scalar. Okay, fine. So let us see if it's actually possible to do this. Is it actually possible to write every matrix, every quadratic form in terms of a matrix, right? So let's ask an even simpler question first. For this quadratic form over here, we have written down this matrix multiplication, this quadratic form as a matrix multiplication. We can ask if this is the only way to do it. For example, is there another way I can construct this matrix A such that the overall product, okay, ends up computing to the same? Okay. For example, you can also take this matrix. You can take x1 square. You can take the following matrix: 1 1 0 0 0 1, x1 x2 x1 x2. Okay, with a simple matrix multiplication, you can actually check that this again computes to x1 square plus x1 x2 plus x2 square. Okay, so it again computes to the same thing. So as you can see that this matrix here is different from this matrix. Here we had 1 in the instance the upper triangular portion, but here we have a 1 in the lower triangular portion, not the upper triangular portion, right? So this is also a valid matrix for this quadratic form, right? For that matter, I will urge you all to check that it's possible to do even the following. You can actually write 1 half 1 x1 x2 x1 x2, right? You can also construct the matrix as follows. Once again, you can just do the matrix multiplication and check that this again computes to the same quadratic form: x1 square plus x1 x2 plus x2 square. Okay, right. So it does seem that there are actually many possible quadratic forms. In general, this is the most general matrix that you can write that will evaluate to this quadratic form. Okay, once again you can easily check this. Okay, just compute this and you will actually get it to be the same as this quadratic. So it would seem that I can pick this parameter A to my liking. I can set it to whatever I want. If I set A to be 1, I get the very first matrix that I have here. If I set A to 0, I get this matrix, and if I set A to half, I get this matrix. Okay, very clearly, of all the choices of A, this is probably the one that I would prefer, because this results in a symmetric matrix, and we have a very powerful result on symmetric matrices having to do with the spectral theorem. Okay, so in the next portion of the lecture, we will try to formalize this. We'll try to look at this slightly more formally, and then we'll explore the connections to the spectral theorem.